So, hello, everybody. Thank you for being here. My name is George Markomanolis. As you can see, many people have contributed to this and more slides. And we're going to discuss a bit about the HIP programming, the ecosystem, and how to program with HIP. So I'll mention a bit about the Radeon Open Compute Platform, the ROCm basically. AMD GPU programming concepts, kernels, memory, and structure of host code, device management and asynchronous computing, device code, shared memory, and thread synchronization, and GPU software, shared memory, and some atomics a bit. So about the ROCm, if you have worked with ROCm or even tried to install it, you can see that it's constituted by many components. So it's not something like a simple one thing. So if we can go from down, you can see that we have deployment tools, have a validation suite to see that ROCm pass some tests, some ROCm data center tool to use it, the ROCm SMI to see the GPUs, and then it's drivers, development toolchain with compiler, profiler, tracer, debugger, HIPFort, there's also HIPFort, and we'll talk a lot about the HIP API. My colleague will talk also about OpenMP. We're not talking about OpenCL. It is running, but we're not really using it a lot. We have libraries for many things. So now we'll discuss about how to use libraries from NVIDIA to AMD. Framework support, we support Cocos, Rasa, PyTorch, and TensorFlow. So don't miss on Friday a presentation from my colleague about introduction to ML frameworks. Cluster deployment, Singularity, Kubernetes, Docker, and Slurm. So as you understand, for supercomputers, we have Slurm scheduler, but also there's some work ongoing with containers. About operating systems, as you can see, support plenty. Usually we have Slash on the HP systems, some desktops have Ubuntu, and of course there are some other systems. And there's benchmark and application support, like MLPerf, HPL, HPCG. I have to mention that we are one of the, maybe the only vendor that has open source HPL, HPCG, and life science, geoscience, and physics. So ROCm is it's a huge ecosystem, I would say. We know that installation sometimes can be a bit tricky, but in order to make it all work, and it's open source everything, so this is another advantage that people can contribute also, etc. So through the heterogeneous system architecture, HSA runtime API exposes the necessary interfaces to access and interact with the hardware driven by AMD GPU driver, and this is how everything works. And with ROCm 5, we have a new features activated and improved, and support also RDNA GPUs, remote access through AMD Accelerator Cloud, MI200 optimizations, 64-bit matrix operations, and improved cache, and improve the latency and kernel performance, and also enable SPC applications and ML frameworks on AMD Infinity Hub, which can provide also containers there that you can use directly for a signal performance. And streamlined and improved tools, increasing productivity, as we're going to talk also to the next presentations. Now, ROCm, Radeon Open Compute Platform, and I mentioned HIP, right? HIP is a heterogeneous compute interface for portability. It's part of a larger software contribution, from ROCm. The install instructions and documentations can be found in this link, and the ROCm package provides libraries and programming tools for developing HPC and ML applications on AMD GPUs. And we'll mention later about the libraries also. All the ROCm environment and the libraries are provided from the supercomputer. So when we say about installation instructions, usually you don't need them. Only if you test on another system smaller that you want to install your stuff, or install the latest ROCm version maybe yourself to test something, right? And as I said before, the SSA is a runtime that basically, when you set commands to GPU, the SSA decides how to interact with the GPU. So let's talk about some AMD GPU programming concepts. People who know about CUDA, they'll be familiar with some stuff. Not almost everything, it depends. Now, about HIP. HIP is portable. What do I mean portable? They have C++ API, host and device code, and it depends on what hardware you have, or it will include the CUDA header and will use ENCCS and run on NVIDIA CPU, or they will include HIP runtime and use HIPCC and run on AMD GPU. So basically, a HIP code is portable. There can be some exceptions depending on what is code, but usually it's really portable and a really small overhead. So HIP is open source, as I said before, provides an API for an application to leverage both GPUs. It's really easy to convert codes, we'll see that later, from CUDA to HIP, and supports a strong subset of CUDA runtime functionality. Now, as I said before, there's also host and device side. The host is the CPU. The host code runs on the CPU. Usually is a C++ syntax and features. An entry point is a main function. And HIP API can be used to create a device buffer, a move between host and device, and launch device code. While on device is the GPU, right? And the device code runs on the GPU, and it's C-like syntax, as we'll see later. And device codes are launched via kernels, and instructions from the host are enqueued into streams that we'll mention later what streams, and that they enqueue the tasks and they're completed by the order, etc. Now, HIP API. So people who know CUDA, in this slide, you can replace the HIP with CUDA, and then you know the commands. So basically, during this talk, we'll mention basically all of these commands. HIP set device, right, to set which device you use, memory management, reserve memory, streams, create streams, destroy, etc. Create events, what's a global function, device function, and various other things, shared memory, and error handling. So we'll talk about this during this presentation. Now, kernels, memory structure, and cost code. Now, in HIPs and CUDAs, maybe you know, kernels are executed on a 3D grid. So you might think of it as like a mess of points, right? But it's not required, but it's easy to think like that. So the grid is what you map your problem to. It's not a physical thing, but can be useful to think that way. And AMD devices, GPUs support 1D, 2D, 3D grids. But most work maps well to 1D. It depends on your problem, basically, and how you want to organize it. Each dimension of the grid partitioned into equal-sized blocks. Each block is made up of multiple threads, and the grid and its associated blocks are just organizational constructs. The threads are the things that do the work, right? This is to do the computational work. Now, if you are familiar with the CUDA already, grid and block structure is very similar in HIP, and I will show you a table terminology. Now, as you see here, I'm not talking about the OpenCL. CUDA and HIP, the grid is the same terminology. Block of threads is the same. The difference is that the thread, in HIP we call it a work item, but sometimes we call it also thread. But the big difference is the warp in CUDA now is wavefront. And one big difference is that the warp in CUDA is a length of 32, and in AMD is 64, the wavefront. So this is something quite significant difference to remember. Okay, let's see now the blocks of threads in 1D. So you see here like that. I think one moment. No, sorry, I have to go back. So you see here that the different colors is a block of threads. And now threads in grid have access to the respective block. Okay, so we can say that this is one block and this is another block with the colors. They have the thread ID x.x. So this is what's thread is here. The block dimension is here, it's like a 4, and the number of blocks in the grid. Okay, so here, for example, it's like 8. So you have some variables that can help you identify my location here. Okay, to define which the global location during all of this 1D or 2D, as we'll see in the next one. So with 2D, each color is a block of threads, okay? So that's easy to mention. So it's small square with the cursor, if you can see, is a thread, okay? So it's small square. And the concept is the same in 1D and 2D. In 2D, each block and thread now has a 2-dimensional index, right? Threads in grid have access to their respective block IDs, block ID x.x and dx.y, okay, because you have now different x and y, and the thread ID becomes also adx.x and adx.y, etc. So this is now becomes not complicated, but a bit more different how to calculate it, my thread position, etc. For the global position in this, let's say, grid. And let's say about the kernels. Now, this is a simple balancing parallel loop. What we have here, basically n times, we have this array, and we multiply by 2, okay? And this device function that will be launched from the host program is called the kernel, and it's declared with a global attribute. See here, this is a global. Kernel should be declared void, so not like integer or something else. And all threads execute the kernel's body simultaneously. So this is not always 100% true, but you have to think that here you have a lot of threads executing this command. Okay, and basically each thread uses its unique thread and block IDs to compute a global ID. So each it's unique, and there could be more than n threads in the grid, of course, and and this then here, this one is not declared here. This is the in device declared in memory, and now multiplies this by 2. So this balancing parallel loop in CPU is converted to this in the GPU. So we need to have the global, the void. We need to find, depending on the problem, of course, but usually you want to find what's my index on this grid and do an operation that I need with something useful. And something else that, of course, always you have to remember that when you want to take performance from a GPU, and especially from a MI250X, which is strong GPU, you need enough workload. So this is a tiny, simple example, okay? If you compare GPU's performance, always you need to remember the utilization, that I have enough utilization. Now, kernels are launched from the host, and as I said, here's we'll create a DIM3 type threads, and this is the 3-dimension of a block of threads. And basically, we say here is kind of 1D, but we define 1 and 1 to the other indexes, and we define the dimension of the grid of blocks, which basically will play with the program size and how many threads we have per block to identify the grid of the blocks. And how we call.
So, sorry, George, to interrupt. There's just a question from the audience, maybe. Does anyone want to ask by voice?
Yeah, George, just a naive question with your previous example. Couldn't there be less threads than elements in your vector?
Yes, less elements. Yes, I said that the n can be more. You mean if it's less, you don't utilize a lot of GPU? It can, of course, it can be, but the performance will not be what you expect. Also, with not enough.
Sure, but then your code will break, I think.
If the n is less than the threads, you can put some, let's say, safeties, not with this code. You can put some safety to try to control it, that you don't use everything. I think you can do that and not break, but you will not get the performance I would expect.
Okay, thank you.
Welcome. How large kernels, heap large kernel, GCL, the kernel name, the blocks are defined here, the threads, okay. This is how many bytes of LDS, this is the shared memory that we'll talk about later. This is on its compute unit. Streams that we'll talk later. By default, we use the zero. The zero equals the null stream, which means that everything will be kind of serialized and nothing overlapped, as I show you later with streams. And then this is some argument of the kernel. It's not something that's always these things, but whatever the kernel arguments asks. Now, as always, when we're presenting that this is the way to call, it also can be called as in CUDA, right? If you use this, it's the same with this one. Because at the beginning we had this, but now also this is the triple server supported, so you can call it also like that. In this way, you don't have to make many changes in your code, when you convert especially from CUDA. Now, simple operations, while blocks and threads. There's a natural mapping of the kernels to the hardware. Blocks are dynamically scheduled to compute units. All threads of a block executed on the same compute units. The threads in a block share the LDS and L1 cache. So the L1 cache, they can exchange also some data, and executed in a 64 wide chunks of wavefronts, and they're executed on SIMD units. Finally, if a wavefront stalls CPUs, then they can quickly context switch to another wavefront. So basically, it's like natural to talk about these operations. And a good practice is to make the block size a multiple of 64 and have several wavefronts, and with 256 threads, for example, per block of thread. Now, this is not a generic advice. It depends on the problem. I had cases that even 1000 was really good. So I cannot give a generic advice. This is just a hint. Now, device memory. The host instructs the device to allocate memory in VRAM and records a pointer to device memory. So basically, what we do here is 1000 double malloc is for the host memory, okay? And now here, usually, if you want to do that with D in the front, we can define the device just to recognize, to remember by heart that this is device. If you see the code, and we say like, yes, heap malloc this and n bytes, okay? So allocate n bytes on device. And you can do other stuff here, and you can free the host memory and free the device memory. Okay, so this is a simple way to allocate memory on the device and free it. Just don't forget to free it because it can cause some issues. Now the host queues memory transfers. So to copy data from host to device, okay. So this is the host, the device, the bytes, and this tag says heap memory copy host to device. Now, if you want to do the opposite from device to host, you swap these two from HD to swap them, and you write here MEMS device to host. And copy data from one device buffer to another. You can also do this, now it's device to device, but this is between devices. Okay, so we'll see later also some asynchronous stuff, etc. So there are plenty of approaches. Now also device memory can copy static sections of arrays. Now this is like static sections. This is more complicated, not always use it, but this is an example is to copy the 2D, right? Pointer to destination, bits of destination array, pointer to source array, number of bytes in each row, number of rows to copy, and copy from host to device. This is not something that I will see quite often. This is more as an example to say that it exists, but maybe it depends on the code, how useful it is. Now, error checking, I would say that's quite useful because sometimes we are not sure that something happened. Most heap API functions return error codes of type heap error_t. And so if you do heap malloc, and you define this, the status 1 contains the error code, or it's success, heap success, or something is wrong. Same with heap memory copy. If API function was error-free, it returns heap success, otherwise it returns an error code. And how you can get that? You can say heap get last error, the last error of the previous commands, or heap pick last error, and define it like that also. The get last error takes the previous error, and you have it in status 3, and it cleaned the error. It says, okay, I got the error, and I cleaned it now, while pick doesn't clean the error. So you need to handle it later in the code. And now a classic example of how many places in AMD is this command, this macro that you define a heap check command, okay, and you inside here you say the status of the command, and if the status is not success, then print the error. With heap get error string, you can take some useful information. What is error? I don't know if someone has any question until this point. Now, because we'll talk about different parts, right? Let's put it together. So we do malloc, okay, and we do heap check the heap malloc. So check if the heap malloc failed, right? Because maybe you define you don't have enough memory, for example, the GPU, right? One maybe classic reason. Then heap check the heap memory copy that to the device. If the heap memory copy really was it worked, then launch the kernel, okay, and get the last error from the last kernel, and memory copy results back to host and do something with the results. So the useful workflow is like, not always, we'll copy some data to the GPU, we'll run the kernel, we'll do something there, and we'll return back the results. It's just a common, let's say, practice. And of course, yeah, free them also, okay? And also check if there's any problem to free the device memory. Now the global here, the global is the kernel, is the kernel that we saw before, and the heap check is what I saw before. So now you saw that the previous slide that we present piece by piece, how you assemble them together. And of course, you saw here the heap runtime, right? The include to have all the access to the heap malloc and the heap commands, and how all of them work together to bring you a concrete example. Now, vector addition, let's discuss an example dimension, okay, 16K times 16K, 16 blocks of X and Z dimensions, and 1 for Z dimension. And what we saw here is that we do malloc for a host A, B, C arrays. We initialize them, and we do malloc on the device, okay, and then copy from the host device, okay, the B and C, because this is a vector addition. And then we have calling like, we have to call a kernel, and we'll play here again with the problem size and the threads per block, as you see here. And here's the height, because now, as you saw, we have 2 dimensions. We use 2 dimensions. So here, height, this is the width, and the height divided by threads per block on the y-axis, okay? And here we have the threads per block. We don't use a set memory or stream, and what we need to define as argument in the kernel. And then we copy from the device to host the array, the A, which is the result basically. That's why here we sent only B and C, right? Because the A is the result, that the A will take it from the GPU. Verify the results here and free the 3 device arrays. So this is how it goes easily. Now this was like I will show you, I think in 2 days, the profiling, just to show you You can use the ROCprof. This is the binary the vector addition binary, and you can do statistics for the heap trace, and you can see, for example, for some commands, the total duration, nanoseconds, average per call, because here you see how many calls, and the percentage. So here you can see 90.78% is memory copy for this example, for example, which means that the computation is quite small, the size, etc. And I'll show you also the Perfetto. Perfetto is, let's say, web-based visualization of traces that you can see here, the heap memory copy, and another heap memory copy, another memory copy, and some other aspects of your application to understand what takes long time, etc. So this will see them in the profiler's day. And device management and asynchronous computing. What if you have multiple GPUs in the system, right? This is the real case for Dartel, Lumia, for everything. So if you know CUDA, you know this stuff, or even heap. So how you can query number of devices. Let's say number of devices 0. Device take the count how many devices we have. Okay, and host tells the runtime to issue instructions to a particular device. So for device 0, heaps a device. So the heaps a device, this one says use the 0 GPU. It can be 1, 2, and basically I will mention tomorrow the architecture of the MI250. It can be seen as 2 GPUs, so have plenty of them per node. How host can query what device is currently selected is this one. Okay. The host can manage several devices by swapping by the currently selected device, but this is kind of serialized. And this is what serialized, I mean, select this device and then this device. Well, when with MPI and the PI rank, you can play and do that with multiple GPUs. Device properties, depending on what you're doing, sometimes it's really useful. Sometimes you don't use it so much. The host can also query device properties. So you define the props here, and you take this command. Take here, you take the device ID, but you can take a lot of information, like what's the architecture of this CPU, what's the clock speed, the total VRAM, the device name, etc. You can find all the information here. What you can ask here, okay? So sometimes it's really nice to do that if you want to, let's say, to reserve memory depending on how much free it is, or to know the architecture, etc. Now, something really important: blocking vs non-blocking API functions. The kernel launch function heap launch kernel DGL is non-blocking. So when you call a kernel, the host will continue directly. Even nothing was executed yet on the GPU. So after sending instruction data, the host continues immediately. If you know the kernel will take some time, this is a good opportunity to do some other work, like MPI communications on the host, for example, or something else. However, the heap memory copy is blocking. The data pointed into the arguments can be accessed modified after the function returns. So if you, I will show you later, if you do kernel launch and then heap memory copy, and then you can be sure that that the kernel has finished after this heap memory copy, because it's blocking. Now, there is also non-blocking memory copy, because sometimes you want to send data that you don't need them immediately, but you want to send them for something later. So you can use heap memory copy async, and now we have the stream. Okay, the host device, the bytes, host device, but the extra is a stream. One moment. So if you see the heap launch kernel, this function takes an argument heap stream underscore p, and we'll talk about streams later. It is not safe to access modified arguments of heap memory copy async without some sort of synchronization. So if you execute this and you try to access something that is used, you need to be sure that this has finished, and we'll discuss that. So as you understand, it's quite easy to do a mistake without knowing that's a mistake, just to be sure what's blocking, not blocking, and sometimes even check your data if you're not sure while they develop. So let's put them all together now. And we have again the previous example, the heap malloc, a memory copy, latching the kernel, get last error, and heap memory copy. And what happened is here, the host waits for the kernel to finish here. So this is the difference with heap memory copy. Because I will show you later, there's another command to put here to be sure that it's finished. But if you have something to take from the GPU to the host, then with this command, it's also like a barrier, like a synchronization. Okay. So let's talk about streams. A stream in heap is a queue of tasks. Okay. Kernels, memory copy, events. Task executed in a stream complete in an order of that stream. Okay. So it's like first come, first serve for the same stream. Tasks being executed in different streams are allowed to overlap and share device resources. So you define a stream, you create a stream, and you destroy a stream. It's quite that simple how to create it. Now, passing 0 or null as a heap stream argument to a function instructs the function to execute on a stream called the new stream. No task on the new stream will begin until all previously enqueued tasks in all other streams have completed. Okay, so blocking calls like heap memory copy run on the null stream, which means on the null stream, when you run something, you assume that the rest are finished, and then this runs. And let's discuss a bit more about streams. Now, let's say we have 4 small kernels, and I use no stream. You see here is 0, 0, 0, 0. Okay. Even though these kernels use only one block each, right? They will be executed in serial on the null stream. Okay. Now, of course, this is a demonstration. It doesn't mean that there is no gap between them or something else, right? Or here they are equal, and we don't know what's a kernel equal. Let's say time taken, but maybe something different. This is demonstration and only. Now, if I add stream 1, stream 2, stream 3, stream 4, I give them the opportunity to overlap. Here they overlap perfect and they are equal. Of course, the case can be different. Kernels must modify different parts of memory to avoid data races, right? You cannot access the same memory from the different kernels. And now with large kernels, overlapping computations may not help performance. What I mean, imagine this is my kernel 1 takes half GPU, and this is another half. Then these have no resources to run, and they'll be serialized. So don't expect that let's create many streams and let's do things. You have to calculate that the GPU has enough resources to run your application. And so that's why you always have to think, if something doesn't work, that I'm sure that I'm doing stuff correctly before I think that, oh, something is broken. Then there is another use for streams besides concurrent kernels, overlapping kernels with data movement, right? Now, AMD GPUs have separate engines for host to device, device to host memory copies, and compute kernels. These 3 different operations can overlap without dividing the GPU's resources. The overlapping operations should be in separate non-null streams. And then the host memory should be pinned. And what's pinned? So host data locations are pageable by default, right? The kernel can decide what to do. And the GPU can directly access host data if it's pinned instead. So what do we mean about this? Allocated pinned host memory, we'll use heap host malloc here. Instead of using malloc, we say heap host malloc, because then the GPU can directly access and it is faster. And also to free the memory is this. Now, host to device memory copy bandwidth increases significantly when host memory is pinned. And this is good, and we can see that. It's good practice to allocate host memory that is frequently transferred to from the device as pinned memory. And what we mean by that? If I do heap host malloc for one transfer, it's not a lot of gain. You need to HIPFort malloc when you know that you transfer quite a lot of data many times to see the benefit. With one transfer, you will not see a benefit. But with plenty, you will start seeing that the bandwidth is improved. And this is quite good. Now, streams suppose we have three kernels, which require moving data to and from the device, right? So I have three memory copies, no streams, and copy from device to host, and you can see them all serialized as they should. Now, turning to asynchronous memory copies, you see here memory copy asynchronous, which means they have streams, and these streams, you can see this, okay? That slowly they overlap because they have one engine and they have to be in different streams. You can slowly see that host device overlaps to my kernel, and here I have full overlap of these three engines, okay? Now, of course, this shape is perfect and that everything is same time, etc. Again, this is an example and not really something realistic always. More to show you that how good is to overlap, and because this will take your code to be quite faster. And synchronization. How do we coordinate execution on device stream with host execution? Synchronization is the answer. Now, this is a classic, I suppose you have seen also in CUDA. This is heavy-duty sync point, blocks host until all work in all device streams has reported complete. Okay, this is a classic to wait that everything finishes and then I continue. While here, this blocks host until all work in stream, a specific stream, has reported completed. Okay, so this is the difference if you want to wait for a stream to finish. Can a stream synchronize with another stream? For that, we need events, and yes, this can happen. Now, event, we declare it like that, and we create it with HIP event create, and we queue an event in the stream. So we say event is like to record something that in event happened. So when you do HIP event record, event and stream, the event records what works currently enqueued in the stream. When the stream execution reaches the event is considered complete, and we destroyed it with HIP event destroy. And that is more about HIP event synchronize event, block host until event reports complete. So imagine you have a strange workflow in your application that you need to reach at this point before you do something else. And this is you create an event to be sure that you will not continue before this happens. Only its transition point with respect to the stream where event was enqueued. Now, something useful to measure the timing is HIP event elapsed time, which measures the time between two events. So you put the one start before event and then end event, and when the end is completed, then you do this command, and it turns the time between two events, start event and end events, completed. Can be useful for timing kernels, memory copies, etc. And a HIP stream wait event is with stream and event. It's no blocking for host. Instructs all future work submitted to stream to wait until event reports completed. Okay, so this is a nice way to control some dependencies in the stream. Primary way we enforce an ordering between tasks in separate streams. So this is quite, it's not really often, I would say, but maybe to someone could be useful. A common use case for streams is MPI traffic, right? So here is like load the kernel to the compute stream. So as you see here, compute stream, load the kernel. Copy hello data to host, asynchronous copy, okay? Device to host is here. Now, HIP stream synchronization, wait for data to arrive, okay? So in that stream, wait for data to arrive, here we wait. However, we can do API data exchange communication from the host, right? Because this is not blocked. And send new data back to device, okay? From host device here. So while we wait here for this to finish, we can do MPI, and it's like overlapping. It's overlapping also with the kernel, right? So this is about a common use. It's like to overlap with the MPI communication, for example. In general, I would say if you understand the concept, you can design your workflow as you wish and try to overlap cleverly what else you can do concurrently. Now, with GPU-aware MPI, the host device traffic can be omitted, okay? So some synchronization, the data on GPU and local computer are ready, so everything is ready. Then exchange, okay, and this is on the device, the buffer. You latch the kernel, and then you wait, and then the MPI clearly overlaps. So this is a good benefit of having GPU-aware MPI stack and use like that. As you know, it's crucial that on these systems, the buffer and MPI communication is on the GPUs. It will be, in general, more efficient and can be more easy to handle, depending on the case, of course. Now, device code, shared memory thread synchronization. It seems that I'm getting out of time slowly. Now, HIPFort, okay, this is, I will mention later, this is a script wrapper that compiles basically, makes two compilation passes through source code. One to compile host code and one to compile device code. Now, the global functions we mentioned, okay, the identity points to device code and called from hosts. Code in this region will be executed on SIMD units, while device functions can be called from global and other device functions. Cannot be called from the host, okay? So it should be or from another kernel, or from the device function, not compiling the host code, and essentially ignored during host compilation. If you want to be called from host and from kernels, you should define it host device functions. Can be called from global and device and host functions. And when execute SIMD units, one called from device code. Okay, that's the difference. So we see cases that people need any of these cases. So all of them are quite useful. Basically, to my opinion, you need to play a bit with it to understand it better. So hands-on with them works quite better. Now, SIMD execution on SIMD units, be aware of divergence. So when you have the if-else, right, wavefront encounters an if statement and evaluates conditional if true continues, if false also continues, but with all the instructions replaced with no ops. So if this happens, in a wavefront, it's called as thread divergence, and I'll show you in a simple example. Generally, wavefronts diverging from each other is okay if it's different wavefronts, but if it's the same, can impact performance, as I'll show you here. We have this, right? Modulo 2, multiply by 2, multiply by 3.14, and this is what happens, right? So this, in this case, is false, so it says no op, and it continues here. While here, this is true, it does this operation, and does here no op. So here, the performance will be impacted. Of course, depends how big is your example, but it will be impacted. So that's why you have to be careful in the kernels with the branching, how you do it. Of course, sometimes it's difficult to avoid for huge kernels, but have it in your mind. Memory declarations in device code, malloc-free, not supported in device codes. Variables arrays can be declared on the stack. Stack variables declared in device code are allocated in registers and are private to each other. Okay, so to each thread. So it's not something that you can share. However, threads can all access common memory via device pointer, but otherwise do not share memory. So important exception is the shared memory. And what to say with this is that when we do use a shared, allocated once per block in LDS memory. So it's shared and accessible by all threads in the same block. Access is faster than device global memory, but slower than register. Okay, register is faster, LDS slower, and global memory, HBM, is much lower. although it's fast, right, the peak, but compared to the other kind of memories. And must have size known at compile time general. So the shared memory stuff, the compiler should know the size of the memory during compilation. Now, I'll just here an example, okay? This is a kernel that has this argument, and this we define shared memory, okay? Array of doubles shared in this block. And we'll say here the following. I want to find my ID, and I do each thread fills one entry, okay? We take from here the DA, the device, and we assign it to SA. And we swap and say the DA equals 255 minus my thread. There's a problem here though. What's the problem? I see it's 256, okay. Maybe a wavefront is inside here, the first one, okay, 0 to 63, but the second is not here. So what I'm reading here, I don't have all this data yet. So what I want to show here, something is missing here. And what's missing here is that these sync threads, okay, inside the kernel, only want to synchronize the threads, you run this to be sure that all wavefronts are here. So I have the data for this to continue. Otherwise, it can crash, it can be garbage, it can be anything. Probably crash, I suppose, or not. But in any case, you need to be careful to be sure that you have the appropriate data when you continue here. Okay, so sometimes this can be tricky. Also, just to mention that the shared memory, as I said, is faster than HBM, but you need to be sure that you have enough to use memory. And there's a case not to be able to utilize the GPU because you require too much shared memory and you have to serialize some tasks. So that's why you need to be careful. Thread synchronization, as I said, sync threads blocks a wavefront from continuing execution until all wavefronts have reached. Memory transactions made by a thread before sync threads are visible to all other threads in the block after sync threads. Can have a notable overhead if called repeatedly. So be careful with that because, of course, it's a synchronization, right? Best practice, avoid deadlocks by checking that all threads in a block execute the same sync threads instruction. And what we mean with this is that so long as at least one thread is in the wavefront encounters sync threads, the whole wavefront is considered to have encountered sync threads, okay? If one thread of all the wavefront of the, okay, there's 64, then all of it is assumed. The wavefronts can synchronize at different sync threads instructions. And if your wavefront exits a kernel completely, other wavefronts waiting to sync threads may be allowed to continue. So depending on what you are doing, you have to be careful that it's a behavior that you want or you don't want. So when you go on this level, yeah, you need to triple check what you were doing. Now, GPU software and shared memory. Here, HIPFort is a parallel script basically that uses LLVM and flags and to compile this CPP file. Okay, and here I define offload arc architecture. For MI200 series, the architecture is called GFX 98. Okay, so if you have a system with many GPUs, it's good to define this to claim I want to run on MI200. Okay, now something really useful, if you define this environment variable, you can see a bunch of useful information, compile and link lines and various paths. So if I do this and then HIPFort, I can see the heap path, so this is maybe order execution, and the arguments that I use, and what Clang does, the options, etc. And also you can use HIPFort-v to print some information. It's a bit different. And with the command hipconfig, you can see many information about environment variables declaration. So for me, this one many times have helped me to understand what's happening on the background. Now, of course, I'm not here to talk about assembly. I just want to mention that we provide this option. You can expect the ISA that was emitted by HIPFort. The command is the extract kernel that's provided by ROCm, and is roughly equivalent to LLVM object dump. And when you do this example, you can start seeing the assembly. Of course, you can see that it's like a vector operations, some floating, some unsigned integer, etc. But I'm not here to talk about assembly this talk, but I'm more to show you that there's an option, and sometimes you can find errors that happen, etc. Especially with our debugging tools. Querying system, ROCm info. Queries displays information on the system's hardware. More info this link. Querying ROCm version. So if you basically cut this file, you can see which version of ROCm you have. And ROCm SMI is the most classic one that we use here to see. But first to mention that with ROCm SMI, you can change frequencies, power usage, and fan speeds, but only with sudo access. So it's not something that probably you will do. And with ROCm SMI -8, you can see all the options, or looking here. And now here you can see the temperature, you can see utilization, power cap. Here the performance is manual, usually it's in the auto, and some clock speeds, etc. Just to mention, because maybe you have question, if in a node we have like Dartel, you'll be able to see 8 GPUs. It's 4 GPUs basically, but I will explain, I think, tomorrow. The second GPU here, I think the second GPU will not have temperature because they are connected per pair to GPUs. So only one gives temperature and the other not, and again the other yes. So it's not something that's error, it's something that's how this works. Now about the GPU libraries, probably if you have, maybe you have heard these things many times. Now I have an example of HIPFort. The HIPFort have the ROCblast and a QBlast. So what we call HIPFort, if our device is AMD GPUs, it's called the ROCblast API. If our device is NVIDIA, it will call the QBlast. This is the portability. When the library starts with ROCblast, it's AMD GPU, and when it's like HIP, it's an interface between ROC and CUDA. So when you run, when you coding with HIP libraries, you know that you support both. So it's good to target the compatibility. Maybe some people prefer to run ROC in case there's any tiny overhead, but usually there's not. Usually there's not so much cases, I would say. And we have many libraries, like as you know from CUDA, from NVIDIA, QBlast, Q50, QRAN, Thrust, the corresponding is ROCblast, ROC50, ROCRAN, etc. And most of the API calls are supported. Also have a sparse, linear solvers, etc. And there is here a good guide of HIPFort guide for a complete list, ROCm developer tools and HIP. So we have enough libraries that you can start using them and porting. Now, here I had an example about the ROCblast. There's no need to install it. It's already on your systems when you have access. Basically, linear algebra functionality, AX speed, MB, etc. Use HIPFort for compatibility, and it's the same about the wrappers. And here it was just an example that you do the HIP malloc, etc. You define the array and you initialize it, and you copy host arrays to device, and you make the ROCblast handler. You create a handler, and you do the DACP. This is the DACP example, and then you destroy. And this is how easy it is to use the ROCblast. Okay, and of course you have to link with the last ROCblast. Usually this is automatic, but you need some maybe linking help from you sometimes. We will see that. And there is plenty of libraries, right? BLAS, for BLAS, for FFT, as I said before, alternative solvers, parallel primitives. And we have machine learning frameworks, TensorFlow, PyTorch, Caffe, machine learning libraries, MIOpen, Tensile, Rickley, Horovod, and benchmarks, MLPerf, and DeepBench. And something else that that was a bit later about the set memory that I said before. We can use set memory that sizes are not known at compile time, as I said before. So declare one array using heap dynamic third macro used for all dynamic LDS space. Now, this one, let me see if, sorry, it changed. This one is a bit different than what I said before. You can do some tricks in order to avoid to know in advance. It's like this one, heap dynamic third, okay? Dynamic array of tabs third in this block, okay? So we do that while you don't know exactly the size, third memory can work without, to compile without knowing the size. But it's something that you can try it if you want, etc. Now, atomic operations perform a read-write of a single 32 or 64-bit word in device global or LPS memory. Can be called multiple threads in device code, perform in a conflict-free manner. AMD GPU supports atomic operations of 32-bit integers in hardware. So you do atomic operations to avoid some race conditions, etc. in some cases, depending on your algorithm. Now, float double atomics implemented as atomic cars, compare swap loops, may have poor performance. So there are some indications. And you can check at compile time if 32 or 64-bit atomic instructions are supported on target device, depending on what device you are running. But on a matter of 50X, have a good support. And basically, this is a list. I don't plan to read it, but this one, for example, adds value to this address, and this one replace address with this value and return old value, etc., etc., etc. So sometimes it performs and it's better to use atomics. It depends on the code and what you are doing, right? It's not always. It's about sort of specific problems, but some flags also to improve performance in some cases. There's a lot of GPU programming resources. You can find here in this link, HIPFort, and we'll talk about porting in the next presentation. Rock profiler, he's a rock profiler, but I have new profilers also, and about that I told you about the ISA and the assembly stuff, etc. Could have features not supported by HIP? I think I'm not sure that all of them are correct here anymore. There's no QPTI, right? We use different stuff. Managed memory, there is kind of support. Maybe there's no CUDA preferred or something like that. But you know, to find the latest, because it's changed very often, this is the link to see what's not supported by HIP compared to CUDA. Summary, HIP is an extensive API that covers a lot of GPU programming requirements. It's under continuous development. There's a new release quite often, and it's open source. They can be executed on AMD and NVIDIA GPUs. They're really portable. We have profiling tools that can identify bottlenecks, and it's quite easy to use, especially with previous GPU programming languages. Many things are quite similar.
Sorry, there's a good question. Just one last thing before you start in HackMD. In terms of using AMD GPUs without HIP and OpenMP, what do you think about OpenACC with the Cray compiler?
Yes, there is some support. When it works, seems to be good in some aspects. I don't know if it will follow all the new API, OpenCC API versions. But I think this moment is only Fortran or not, or I'm wrong maybe. I'm not sure.
Right. So they They have adopted LLVM for their C, C++, so they will not have OpenACC with C++, just Fortran.
Yeah. Also, there is also the GNU compiler, right? That AMD collaborates and with Siemens, and they're working also on OpenACC. The answer depends on how new OpenACC API you are using, I would say. Okay, let me start fast. It's a small presentation. Porting applications to HIP, I think many people started already the exercise. So basically, we have the HIPFort Perl, easiest to use, point at the directory, and it will HIPify CUDA code. Very simple string replacement technique, may require manual post-processing. Basically, it replaces CUDA with HIP only if it recognizes the HIP API, the CUDA API. If the CUDA API is supported by the HIP, then it will convert, it will replace the CUDA with HIP. If something goes wrong, it will report that in these lines I couldn't convert, etc. So it's really easy tool to use. The HIPFort is more robust translation of the code, generates warnings and assistance for additional analysis. High quality translation, particularly for cases where the user is familiar with the make system. But I would say that the HIPFort Perl, for many people, is easier to use. Just easier. So it's located, I suppose, still at HIP_bin, and you can do this command, HIPFort Perl, and the CUDA, and this is a new HIPify file. Okay, and you can compile like that. This is a really demo. You need to add flags, etc. Right? So HIPify source code, check it into your favorite version control. Try to build, manually work on the rest if something is not really translated. HIPFort built from source. You have to build it. I'm not sure if it is in the ROCm by default. HIPFort has a unit test using LLVM 44 tests to verify. HIPification requires some headers that will be needed to compile it with Clang. So, for example, here to compile this CUDA file, it's required to have some CUDA headers, okay? And here is the HIPFort in this repository. Now, when you convert, there's some things to be careful. HIPify tools are not running your application or checking correctness. Now, if you have a code relying on specific NVIDIA hardware aspects, like I have my warp size 32 somewhere, hard-coded, I need attention because on Wavefront 64, so the performance will not be as you expect. Certain functions may not have corresponding HIP version, like this one, for example. In this aspect, it was about some data transfer between threads that was not supported on the HIP. So in order to make it work, you go to previous version without the shuffle, and you go down, underscore down, underscore sync, but need some manual things to change. HIPifying can't handle inline PTX assembly, can either use inline ISA or convert it to HIP. So if you use like assembly stuff, you know this cannot be ported like that easily in codes. HIPFort Perl and HIPFort can both convert library calls. What I mean, if you use QBLAS in your CUDA code, it will convert it to HIPBLAS. All the libraries that are in HIP are automatically supported for you. So all the calls to libraries, you have nothing to worry, will be converted. None of the tools convert your build system, such as CMake or whatever else you use. The user is responsible to find the appropriate flags and paths to build a new converted HIP code. This can take some effort depending your CMake. Also, the CUDA is three things, like grep for the number 32, just in case is in your code, do not hard-coded the warp size, define it like more generic, code geared or limiting size of a register file on NVIDIA hardware is not supported, and also some unsupported functions that they have on GitHub, what maybe is not supported yet or is under development. Fortran. Yes, this is still here, but Bob will talk. First scenario is that you have Fortran plus CUDA in the C++ file, this piece of cake. Assuming there's no CUDA in the Fortran files, HIPify this file, compile a link with HIPCC. Second scenario, CUDA Fortran, there's no HIPify equivalent. HIP functions are called from C using extern C. And you see HIPFort, how you can be able to call it this. Yes. So I will not stay here a lot because I think there's a presentation. The strategy here is manual. Manual reports CUDA Fortran code to HIP kernels like in C syntax, wrap the kernel lands in the C function and call the C function from Fortran through Fortran's ISO-C binding. It requires Fortran 2008 because of the pointer utilization. But I will not talk more because this probably is a double thing. Can also target AMD GPUs through OpenMP5 target offload. ROCm provides OpenMP support. Something else, AMD OpenMP compiler, AOMP, could integrate updated improvements regarding OpenMP offloading performance. Sometimes experimental stuff to validate it before ROCm integration. What I mean, if you take here the AOMP and you install it on your system, maybe then the OpenMP performance can be better than the ROCm because ROCm has the latest stable version, while this is about the testbed, and then they go to the ROCm. This is of course nothing that will say like use it. This is to use it if you want to test, not like production. Okay. GCC provides OpenMP offload support. It's coming also to our GPUs. GCC will provide OpenACC. To that, what level of extent we'll see. I have tested more for fun the CLAC from Oakrits. This is OpenACC for LLVM only for C. Fortran and C++ in the future, but I don't know the timeline. But it translates OpenACC code to OpenMP offloading, so they have some functionalities to translate the code. And in some toy examples, it was working, it was not bad. Now, my colleague Jose will talk about OpenMP offload, GPU support. As I said, ROCm and AOMP, there is a more research compiler. There's HP compilers provide offloading support to AMD GPUs. Okay, through OpenMP, HIP, and OpenCC only for Fortran, as we said. And in GRUI compilers, OpenMP and OpenCC offloading support for AMD GPUs. The DC11 supports MI100, and DC13 is the MI200 series. They are working on it and they are improving some features for our collaboration. Here is just a tiny example understanding the hardware options. With ROCm info, you can take, this is a screenshot from the terminal, that here you have 110 compute units. We'll talk about this. The wavefront 64 and 4 SIMDs per compute unit. So a code that's like that in OpenMP, we can define options for Pragma OMP teams target. Number of teams, 220, will be multiple of the compute units. Okay. So multiple number of workgroups with regard to compute units. Thread limit 256 threads per workgroup will be multiple of this. Okay. And thread limit is multiple of 64, and teams times thread limit should be multiple or a divisor of the trip count of the loop. Now, this is not always possible, but it helps the performance if it can happen. So have enough teams with threads to stress the GPUs is a must for OpenMP performance for many cases also.
Okay, let's start then. So today's talk is about getting started with OpenMP offload application on AMD accelerators. So as agenda first, we'll talk about AMD open source software stack, then describe how to build simple OpenMP offload applications. Next, we will expose hybrid MPI plus OpenMP offload application support. Then we'll talk about the runtime report for performance investigation before concluding. So, AMD ROCm is an open source software platform for GPU compute, and it enables all GPU power to accelerate computational tasks. The ROCm itself contains some feature that contain optimized feature for HPC and deep learning workload at scale. We open the ROCm, all the ROCm software stack is open sources, and this enable innovation, differentiation, and collaboration. Inside the ROCm software platform, you have different kind of brick that include benchmark application, cluster deployment, framework support, libraries, programming model, development chain, drivers, and deployment tools. So let's look at some of these. When you look at the benchmark and application support category, you have MLPF, HPL, FSense, geoscience, physics. For framework support, we have a support for machine learning, AI application, we have TensorFlow, PyTorch. We also have Cocos and Rajas. For library, we have support for math library that is included in a ROCm platform. And here we are talking, when we are talking about a math library, it is about BLAST, Solver, Allusion, FFT, Sparse, and so on and so forth. The programming model that are supported through the ROCm platform is OpenMP, OpenACC, and HIPFort. We cannot have a programming model without talking about the toolchain that enable that we can use to build or to port an application on AMD GPUs. So we have a set of compiler, profiler, tracer, debugger, and so on. Next, we have compiler. How many compiler do we have, or which kind of compiler can we use to enable or to effectively offload the code on AMD GPUs? First, we have the ROCm compiler collection, that is ROCm-CC and AOMP. ROCm-CC provides support for both HIP and OpenMP. The AOMP is a compiler developed by the research group in AMD for AMD Accelerator, and it is used to prototype new OpenMP features for ROCm-CC. So basically, the compiler is ROCm, but if you want to test a new feature that are not released yet, you can still use AOMP itself and test new feature. When the new feature is validated and ready to be broadly used, these features are then integrated in the ROCm itself. So that is why we have ROCm-CC and AOMP. Next, we have another compiler that is GNU compilers. And it provides offloading support as well to AMD GPUs. And here, instead of we don't have HIP, in fact, we only have a support for OpenMP and OpenACC. GCC 11, for example, support additionally the AMD ME100, that is GFS 908 GPUs, and GT 13 has additional support for MI200, that is GFS 90A. So as you can see, it is still under development. So expect some, some new release from time to time. We have another compiler as well, that is Siemens compilers, and it is a free compiler based on GCC. This compiler supports all GCC 11 features and additional features from GCC development branch. So it is still under development, and the good news is that it is more advanced compared to the GCC itself, since they combine both existing GCC 11 features plus the development branch feature that are inside the development branch itself. So you can go to this link, follow this link here to access the full list of compiler that you can use to effectively develop or offload a code onto AMD GPUs. Now, if you are using a system that AMD HPC system, for example, you have additional options. That is options that are compilers you can use, and this compiler provide offloading support to AMD GPUs that include OpenMP, HIP, and OpenACC. So what that means for your code, we talk about various compilers, but for your code, what will happen? What is the keyword you need to use when you write your makefile? So for compiler, for example, when you are using compiler on AMD HPE system, you need to specify if it is a C code. You can specify CC, big CC, or FTN for Fortran. And when you are considering ROCm compilers, for example, you directly have access to AMD Clang, AMD Clang++ for C++ code, AMD Flang. And in addition to that, you have access to the HIPCC compiler, which is basically a wrapper for AMD Clang and AMD Clang++. The HIPCC makes sure that, in fact, it's called either AMD Clang or MVCC because it is kind of a smart compiler that knows which hardware you are using. And if the code is targeting AMD GPU only, it will use AMD Clang underneath, or if it is the target is NVIDIA GPU, it will use NVCC underneath. We are talking about HIP, but the HIPCC, you can see clearly that we don't mention HIPFort or something like that just because the HIPCC is the main product that is used, especially when building or when converting up, when you want to make application more portable on both hardware. There is additional tool that you need to consider when you are moving code from CUDA to HIP, but this is not fully covered within this talk. So now, when we have an application, we are offloading an application, or we are developing an application on AMD GPUs that target AMD GPUs. Sometimes we need to access, we need mathematical library functions. Let's consider that you have an application that runs on CPU, for example, and you want to move this application from CPU to GPU. On CPU, you have some call on for gem, dgem, all this math library, but you have also the equivalence of that on AMD GPUs, and these functions are already optimized. And that is what you have here on ROCm library, this column, where you have all of these ROCblat, ROCFFT, ROCsparse, and ROCgen, all these math library are available, and you can use that. Either you are doing the HIP, you have HIP code, or you are doing OpenMP offloads. So that is where we need to briefly talk about the math library. In OpenMP, you can use this library as well when offloading on AMD GPUs. And remember, this library are already optimized. So this talk focused on simpler and hybrid MP and OpenMP offload application building and running on AMD GPUs. So we are talking about OpenMP in this context. So which compiler do you need, or how do you start with OpenMP? OpenMP itself on AMD hardware. When considering ROCm hardware, for example, for C, we said we have AMD Clang, C++ we have AMD Clang++, and Fortran we have AMD Flang. To enable the OpenMP on CPU simple, you have to use -f OpenMP. It's the same when considering GCC. Now, this is a code that is the way you run a code. That's the way you usually run the code. But next, we will move to GPU. To move to GPU, you need to give the compiler a certain instruction in your makefile to make this code run on GPU. So if your target is AMD MI200, you can use the shortcut or -off. You can add a -offload -add equals GFS 19A to be able to offload this code on AMD MI200. Now, if the target is AMD MN100, you can use this shortcut -offload-add GFS 908. If for some reason the shortcut is not working, you can still use the full flag that is available here. But most of the time, when you are using a ROCm version that is greater than 5, technically, if ROCm is well installed, you can use this shortcut. You can add this flag to your makefile to make your code run on AMD GPUs. When considering GCC compiler, you also have some flags that are available. And because GCC is still under development, so expect some change from time to time, but they have different kind of flag. You open this wiki, you will see all these flags available there, especially -f offload. You can enable code generation for target or for host and so on and so forth. So these options are available for this wiki, and you can use it whenever if you want to consider GCC. Now, in addition to this compiler, and in addition to this flag, if you are using Cray compiler, for example, it is basically the same idea. The compiler itself is, as we told, Cray CC, Cray FTN, and so on. So forth. To enable the OpenMP, you need to use -f OpenMP. For C code, and for Fortran, you can use -HOMP or -f OpenMP. In addition to this, to make the code run on AMD MI200, you need to load this module from Cray. If you are using Cray compilers, you need to load this additional module. That is Cray Accelerator AMD GFS 90A to run your code on MI200, or you can use AMD Cray Accelerator AMD GFS 908 to run on AMD 100. So remember, Cray, for example, has some wrapper. Instead of use Cray, CC, Cray, FTN, you can just use FTN, CC, or Big CC to compile Fortran and C or C++ code on AMD GPUs. Here is an example of code building. It is a reduction example. And it is just, you can see that is a simple code. We have a main, and here we insert the pragma target data map to move data. Here, what we are doing that is that when the code starts executing and reach this level, move data from host to the device, which is the GPU. And next, to offload, to compute this loop on GPU, we need to add a target team distribute parallel for. And the goal, after computing, the goal here is to bring back the sum, the value of sum. Because of that, we do the mapping map to and from sum, followed by the reduction operation itself. How do we build this code? We just use a simple ROCm, and we use mdclang simple with -f OpenMP. It is OpenMP code, and we add this to build the code on MI200. And it is simple to build the code. We don't need nothing special, and then you run the code. That's it. Especially when this shortcut is not working, you can still use the long format and produce the same results. Concerning Fortran application, you can, of course, build your code, your Fortran code using AMD compilers. Using AMD ROCm, you can build it. You can build the Fortran code as well using AOMP compilers. You have a possibility to use GCC. But one thing is that many features on Fortran side are still being added to Fortran compilers today. So my advice for you is to use the latest compiler. To always use the latest compiler version and expect the features to be added with every release from time to time. So that's it. So here we have an example of Fortran code that we have been able to offload on AMD GPUs. And it is just a Fibonacci example. And we have a targeted distribute map to array map to and from buffer. So here we are creating a parallel code region. We copy data array from host to GPU. For buffer, we are copying here from host to GPU. And at the end of the computation, we want to bring back the buffer. That is why we have to and from here. Variable sum and sum2 are just private. So next, what we are doing here after offloading this code, we are computing this loop in parallel on GPU with a sum reduction. Here, because we are in a Fortran, when you declare a pragma, you have a directive, you need to close it. So we are closing the parallel compute on GPU here, and we are closing the parallel target team distribute here. So end of parallel code region. And at the end of this execution, data that are marked from, like a buffer, for example, it is marked from, then this data will be copied back to the CPU, to the host. And how do we build this? It is simple as the previous example as well. It's AMD flank -f OpenMP, and we use what can I say? We had a pragma to insert flag to insert of a compiler to build the code for MI200, and then we generate our binary and run it. Simple. Now we can share with you another example with that is use unified share memory. And for unified share memory, there is one thing that I need to talk to you is that unified share memory is evolving. We start with OMP target alloc, but nowadays unified share memory, for unified share memory, you can definitely use malloc, directly malloc in some systems that accept unified share memory. And especially we have over system MI200 that is coming, and this feature will be really useful. So to implement unified share memory, for example, you need to add unified pragma OMP require unified share memory there to start with. You have a device ID, you don't need that if it depends on what you want to do. So you can use device ID. If you use it, then you can use OMP target alloc. But this is optional. You don't need that. If you don't use it, you can directly use malloc, or you can use POSIX align to align memory allocation. So we have two arrays S and Y, so we are basically doing the same thing. And now, if you use OMP target alloc to allocate your memory, you need to free this with OMP target free. Otherwise, just use the standard free to do that. So more and more, I think in the close future, people will start instead of using OMP target alloc, they will just use the code as it is, a malloc, a simple malloc, and a simple free to do unified share memory. So this example is important because when we start optimizing offloading applications, sometimes we need to think when you check the data movement that is going on from CPU and GPU, you might need to reduce the data through unified share memory system. So it is important to keep that in mind. This problem happens most of the time when you are optimizing a code. You are optimizing large application, for example. So how do we build this unified share memory example? It is simple as it is exactly like a previous code. As you can see, we load our ROCm version, AMD client dash OpenMP dash. We specify the architecture, and that's it. So it is simple. It is the same command line. It is just for unified share memory. We need to add the pragma, the required pragma. Now, when I show you some example, a simple example of building of offloading application. Now, in real life, we have some other example that use that called math library. And how do you build it? You just add to your makefile, you add the instruction to your makefile to integrate the call to ROCFFT or ROCblast or whatever you have, whatever math library you are using. So here, for example, this is an example where we are building a code that called ROCFFT. So to build this code, we link of the ROCm library plus the call to the ROCFFT library plus the library AMD HIPFort. That's it. And that is the same syntax. You have the same syntax for any ROCm library you will be using in your code. So if it is HIPBLAST, the technique is always is still the same. So there is nothing additional. So this is important to know when to know, especially when you have in your code a call to ROCBLAST, ROCSPARS, ROCFFT, or any math library we have in ROCm software platform. So we talk about simple application that use OpenMP at low level. So this means parallelism at low level. Now, real life application is not just about OpenMP. It is also about MPI. So we have a hierarchy of parallelism, and that is where we have MPI at top level and OpenMP at low level. This is called hybrid application. So how do we offload hybrid application on AMD GPUs? The technique is still the same, but it is just that we have MPI on top to what can I say, to share our work between different multi GPUs or multi node, and then every node will be running. Every node internal will be running parallel code using OpenMP. So for HPC application, most of people rely on multi-GPU programming, MPI programming model to scale their workload. And MPI is widely used to scale to multi-nodes in HPC applications. But to be able to achieve great performance, you need to add a ROCm aware MPI. You need to use a ROCm aware MPI. You know, a ROCm itself enables various technologies to facilitate the porting of application to clusters. So these technologies are already embedded in the ROCm, and it's a low direct use of GPU pointer in MPI call. So imagine you have a GPU with a node with 8 GPUs, and you have MPI call within in your application. What will happen is that if you don't use the ROCm aware MPI, what will happen is that one GPU will compute something, move data to the CPU, and the CPU now will move data to the other GPUs. But if you use a ROCm aware MPI, what will happen is when one GPU make a computation, for example, the pointer is directly the data, the pointer to is directly used, it directly communicates to the other GPUs. So we have to deliver great performance or optimal performance, we have a direct connection between intra and inter nodes through the GPU to GPU communications. And that is why it is important to use an MPI that is ROCm aware. In addition to this, depending on the application, you might need to do MPI binding. This might be necessary. It depends on the application you have. I will show you one example in a few slides. So it depends on the application you have, but MPI binding sometimes is necessary to get great performance in addition to the ROCm aware you are using. So to start building a multi-GPU, to start using the multi-GPU programming system, make sure that you have multi-GPU on your target hardware. So to check that, you can just use ROCm SMI or any other command you have here to check it that, okay, I have multi-GPU, several GPU on my system here. We have 8 GPUs on the system I'm using here, for example. So now we know we have multi-GPU system. How do we build our code? It is so you can use the same method as we did previously. If you are using Cray compiler, you just need to add the Cray MPH, and the compiler name, the name of the compiler you need to put in your makefile is basically the same thing. And what is good here is that for when you are considering Cray MPH or Cray tools, the library header automatically link when you use this Cray compiler wrapper, FTNCC or GCC. You can, in parallel to that, you can use AMD ROCm or GCC ROCm plus OpenMPI, and here you have access to the standard MPI-CC, MPI-C++, MPI-HIPFort. You can use that to build your code as well. Sometimes, depending on the configuration of your target machine, maybe you might not see MPI-CC or MPI-HIPFort, but that is not a big problem. You can still, as soon as ROCm is installed, you can still use the Clang or Flank Fortran and link that with -L MPI to make your code run to make your hybrid code run without any problem. So you have all these directly, that is fine. But in case the system or something is broken in the system, you can directly link your code, change your makefile, and put this with the -L MPI. And your code you will build your code without any problem. It will work as soon as you have the ROCm installed on the system. This is an example. This is the triad example, and you can see that we have some MPI call in the main code. We have MPI init, MPI communication rank. So we have MPI call here, and somewhere we have OpenMP. That is the target. We are creating a target data region here. So to move data from the host to GPU to the GPU, and then here we execute our loop. We offload the loop on the GPU. We execute it, and at the end we have we collect all the data. We compute the local bandwidth and all this stuff. This is the triad example. So at the end we have the MPI radius. That is the collective communication we are using here. And to finish the example, we have the MPI finalize. So as you can see here, we have a mix of OpenMP at low level and MPI at high level. That is a simple example of hybrid application we are talking about. So how do we build this code? It is simple. Here, for example, I was using the simple Clang, and the link, the library I call -L MPI plus -F OpenMP plus the architecture I'm running on here. I'm using MI200, and I generate my binary. So starting from here, once you have your binary, I can run this code using a certain number of process or rank and so on. So here I am using 16 ranks to run this code. So I run this to run without any problem. Now, sometimes the user or the developer want to run on a specific node. So what do? You need to set the ROCr visible device. Here, for example, I'm setting ROCr visible device to 2 to run on GPU ID number 2 only. So you can do that, or you can specify a set of GPUs if you want. The machine I'm using here has 8 GPUs. So for this example, I'm using 4 GPUs. I'm using GPU 2, 4, 5, 7 to run this code, this triad code, the same way I was running here. It is just the difference that I'm using more GPUs here to run this code, and you can do that. But keep in mind that when you use ROCr visible device, all visible devices are visible to all MPI rank. So is it what you want? If it is not what you want, that is fine. You can still use the srun capabilities. So srun, Slurm has a set of features that enable running hybrid application easily. You will just submit your job. You will specify what you need exactly, and Slurm will take over the rest. So when you have a system like that, you might need to consider two-step run, for example, two level of script. A high-level script that where you build your code, you allocate a partition, maybe one node or multi-node, and you submit the job. The job submission here is done via sbatch.slurm. And what is inside sbatch.slurm? That is what we have. So here, for example, I'm specifying the number of tasks I want, the number of tasks per node, the number of GPU per node, the CPU, the number of nodes, the distribution I want, the time, and so on and so forth. After that, I load the necessary module for my application. If there is any variable you need to export, you export them, and then I run as run with my application. Or you can also use MPI run at this level with your application, the binary plus your application argument to run, to submit your job and run it. So you can launch your job. Most of the time, this happens when you have a big application. You cannot run it iteratively, stay in front of your laptop to run it. You have to just submit your job and go do some other work or focus on something else. So basically, Slurm is your best friend in a situation like that. As soon as you specify exactly what you need, the number of nodes you need, the resource you need to run your code. That's it. So you run your code with Slurm. That is good, but again, keep in mind that when you have a hybrid application, MPI and OpenMP, the MPI you are using need to be ROCm aware MPI. So by default, the OpenMPI is not ROCm aware, but you can build it by yourself. You can build it, or in a data center, for example, if you log in on a data center, you can see OpenMPI that is built with UCS. So UCS, in fact, is that is called Unified Communication as framework, and if you build your MPI implementation with UCS, you make it ROCm aware. So here, for example, we have multiple MPI support for ROCm. We have OpenMPI, MPISH, and MPISH2 as well. And these OpenMPI and MPISH, if you use them by default, you won't get the direct GPU to GPU communication. So you build them with UCS, then you will get it. So when you are doing a performance investigation, or when you are doing you are running an application at large scale, make sure that you have an MPI that is ROCm aware. That is really important. Now, in addition to ROCm aware MPI, and depending on the application, as I said, MPI binding might be necessary to get great performance when scaling. So here, there is an example of binding that is available in ROCm by default. If you load a module ROCm on a data center or on our cloud, you will see, go to this look at this path. ROCm path LLVM bin GPU run. If you go there, there is a script that is called GPU run, and the script can do the binding automatically for you. You don't have to change anything for that. Now, if it happened that for your application, the script is not working, you can still modify it and use it to run, to do the binding, to solve your binding issue. So how this works is that the application is in charge of distributing GPUs, and they compute unit across multiple rank of MPI job. So it uses task set utility to limit the application process to only CPU in the same NUMA nodes, NUMA domain at the specific GPU. So you can check by yourself the NUMA domain. You have ls tuple CPU. You have all these commands there to check all that, and you can check NUMA domain by yourself, and you can check it. You can use available utilities for that. And if you are not happy with this GPU run script, then you can still use it to build your own GPU, to build your own binding script and run it with your application. So how do you use the GPU run? It is simple. You just use MPI run, the number of process GPU run, plus your application, and plus any argument you have. So and you can put all these through, you can use that through the S1, S-batch technology without any problem. You can combine all these together and make it one script that will do all the job for you. Now, we have an application that is maybe running on CPU. We move that application from CPU to GPUs by adding different flag at our makefile, by changing our code, or maybe putting some directive inside the code, inside the hotspot to make the hotspot to complete the hotspot on GPU. We did all this transformation, but there is one thing that is really important you need to consider when moving application or when running application on AMD GPU. That is the runtime report for performance investigation. So, as we said, we have different kinds of compilers. And this compiler, they don't have the same technique, they don't provide the same output in terms of warning or in terms of output from the compilers. So when we consider AOMP, AMD ROCm, OMP compiler, you can use libOMP target kernel trace equal 1 or 2 to profile or to get some specific information from your application at runtime. So when you use target kernel equal 1, for example, it will give you the name of your code at assembly level, the number of things that you are using, the thread limit, register usage. And now when you specify libOMP target kernel trace equal 2, you get the same information plus information related to data transfer, map pointer, and kernel timing information. You can also use another environment variable that is called AMD log level, and we have a value from 0 to 4, and it will give you. So you can use that on AMD hardware, and it will show you a different log from the HIPFort of the HIP interaction between a HIP call you have within your code. It will show you what is going on. Then it will show you the detail of what is the code, what is going on at each step of every HIP call. When you are using Cray compilers, you have access to the Cray assisted debug environment variable. You can set that to 1, 2, 3. And here also you have another view of what is going on your application when you start running. So outputs are different, but I want to introduce you the libOMP target kernel trace. That is really important. It is simple and easy to use. You don't need any additional support. As soon as ROCm is installed, you can directly use it to profile your application. And the data you'll be collecting in technical will help tracking if there is any compiler regression, or it will help you as a developer to identify if there is any performance gap issue within your code. So let's look at this. Let's consider this simple example. This is simple SASP code that we are offloading onto AMD GPUs. We specify the number of teams, the number of thread limit. You don't have to, but I put this number here to show you how this works technically. So when you call this code and you want to time it, we need to put start before the call and stop after that, and we compute the average execution time, and we say, okay, our codelet or piece of code execution time is this. That is exactly what I did here. I have collected the time, but the execution time you have here comprise multiple elements. How to get access to that? First, we export libOMP kernel trace equal 1, and we run the same codelet again. When we run this, it shows that, okay, this code is running on device ID, GPU ID 0, the work group size is 1024, the number of team and thread limit that I'm using is 208.1024. He said the load data storage usage, it is 38 bytes. Scala general purpose register count within my code, it is 23. The vector GPR count is 15. If there is any spill, he will tell you envelope trip count. That is the detail we have when we specify you execute your codelet while exporting libmp kernel trace equal to 1, while setting libmp kernel trace equal to 1. You also have the name of your codelet at assembly level. This is the name of my codelet, for example. You can see it is here. So the name you have at source level is not the name you have at assembly level. Now, let's put libmp, let's set libmp target kernel trace equal to 2 and see what we have. So here we set that to 2, and this is what we have. We run the codelet again, and we have all this information. So we have more information that shows the communication between host and device while running an offloaded code. So you can see that the number of devices. He checks first if the binary is valid, if there is any requirement, device initialization, load of binary, data allocation, data submission, data allocation, and so on and so forth until he runs the code. And after that, we have data synchronization, data delete, and that's it. So what this means for us? Look at this the yellow, the first yellow box. We have data allocation, data submission, data allocation, data submission, and each of them has a cost. So we have a 2 set of data allocation and data submission. Why it is like that? Just because if you remember in my code here, I did map to X, map to from Y. X, because of 2 and 2 here, he need to allocate space for these 2 arrays. And so because of 2 arrays, we have 2 sets of data allocation, data submission, data submission. Now, after this, we have run target team region asynchronously. So this is the pure codelet execution time. But before reaching this level, we need to pay for this first. After execution, we have data retrieve part, we have data synchronization part, and then you need to delete data from GPU, and this also has a cost associated with this. So basically what is going on here is that the pure codelet execution has a time, but before that we need to pay something, and after that we need to pay something as well. So collecting target offload runtime data like data transfer, invocation time, and per kernel time, that is really, really important. If you want to investigate, you want to further optimize your code. If something is wrong, I can definitely know from here that, okay, I'm wasting some time somewhere. Maybe it is not, it is too cost, it is, what can I say? I'm paying more for allocating data and so on and so forth. So profiling this application this way is simple, it is easy, and it gives you useful information quickly. So here we have the pure codelet execution time, and all this is when we aggregate all this, we call that offload task. So that is what you pay before offloading or while offloading a hotspot on AMD GPU. That is what we pay. So this metric here give you, or can I say, an overview of what is going on in an application when you start executing. But it is not just like that. You can also use this metric, in fact, to build a performance model, to build a performance prediction model. For example, you can use the metric to investigate poor performance issue, or check if there is any to do performance gap analysis. You can use all these metrics. Imagine, for example, you have one ROCm version today, you run your code, you have, and you collect the libomp target kernel equal to information. Now you have another ROCm version. You can compare both output and see if there is any huge difference or not. And this will give you an idea about how the code is performing on AMD GPUs through different versions of ROCm, for example. So here we have a set of definition of that are related to each of these function that I showed you a few minutes ago. It is just a set of definition that you can use to identify what is the meaning of each of them. So now let's take an example. Why so let's take two examples to show how it is important to do this low-level profiling. When optimizing data transfer, for example, there are some techniques you can use to minimize data transfers. And this technique includes, for example, using target enter data and target exit data when variables are used by multiple target constraints. So if you have a variable that are used successively by multiple target constraints, you can just aggregate them together and use target enter data. And at the end of the target return, you use target exit data. Another example is that when offloading, you need to choose the right map type. For example, for variable, you can use read-only, write, or alloc. Also, it is recommended to not map read-only scalar variable, for example, to avoid unnecessary memory allocation on the device. So if you map a variable, for example, it will create another data alloc, do another data alloc for that. So it is not advised to do that. It is instead of doing a map for a variable, it is better to use the first private or just not put the variable in the map clause. Now, how do you check the impact of this change? If you want to change this in a code for it, how do you check that? It is simple. You do export libmp target kernel trace equal to, and you run your code before and after this change. Then you compare the generated profile to see what is the cost associated to each of them. Are you paying more for something or not? You will know from the profile you got. When reducing memory allocation, for example, that is another problem when offloading large application. So, for example, map to clause may not be the most efficient way to allocate memory for a variable, for example. We put map to, so sometimes maybe it is just map alloc. If it is map alloc, just use map alloc. Don't use map to, because you don't have to. So understanding the application and how it works is important when you are tuning your application. So instead of using map to, you might need map alloc, for example. Another example here is that when let's consider a temporary array A and B that move data to GPU using map to. So you can replace map to this by map alloc this if you know exactly what these arrays are doing. Because they are temporary array, you don't have to move. You don't have to move the overall. If it's temporary array and it is just for storing some data that are complete on fly on GPU, you don't have to do map to. You just need to map alloc. Or you can replace this by OMP declare target this and OMP end target. Now, how do we check the impact of this change on your code as well? The technique is still the same. You export the OMP trace target and you run your code before and after this change, then compare generated profile, and that's it. You will see the impact of every change you are making on the performance execution, on the code execution, and as a consequence, on the execution time you are getting after this. So to conclude this work, we showed that as of today, this can change in maybe in a few months, but for the moment, we have four compilers exist to effectively offload the kernel on an application onto AMD GPUs. You can use AMD ROCm, you can use Cray compilers, you can use GNU, you can use CMM. Many libraries are available. Use them where possible. You can use module eval. You can use module eval command to check available libraries. You can use module show, module name to see the installation path if needed. Everything depends on the system you are using. some module may not interact well with compilers. In that case, a user might need to provide both header and library path and certain library manually. But in any way, please learn from the compiler help, learn from the compiler verbose output, learn from debug information, and learn from sbatch, srun option. So we have many options available in srun. I put that at the end of this slide, so you can learn from there. You have some option with some description available there for you to be used. And I put some example of binding here that might be necessary for you. So thank you so much. If you have any question, feel free to ask. So if you go to, I think that is called global training. Okay. Here. So if you go there, you have an OpenMP sample, and you can take the GCC SASP GCC, for example, and we can play with that. If you look at the SASP code, you see that it is compiled by default. We use a simple GCC to build it, and we just follow the instruction in HackMD to create the offload version of that. So if you consider the SASP code, for example, you can look at the codelet.c. So the codelet says you need to replace OMP parallel for SCMD with the SCMD, the instruction. If you look at the instruction, we put what you need there. I think it is, if you look at, so after changing the SASP code, you can change the makefile as well, and add, in addition to -f OpenMP, you add the offload target, that dash offload architecture you want to use. That is GFS 90A.
Okay, so this presentation is going to be focused mostly on Fortran applications, and we'll cover a little bit of what was mentioned in earlier talks. I don't think it's a bad thing to repeat because we do cover a lot of material. So Fortran compilers and support have lagged a little bit behind the C and C++ support across the HPC community. And so we'll talk a little bit about the special things you need to be concerned about with Fortran. So there's been several people who have contributed to this. This is just a short list of those who have worked on these slides. So what we're trying to address in this presentation is the different pathways that exist for converting Fortran codes to run on the GPU. We saw earlier that you can, if you have CUDA routines, you can just HIPify them and then call those routines from your Fortran code. Another mechanism that we have developed is called HIPFort, and that gives you a little bit more support for calling some of the functions in the HIP software stack. You've also seen a little bit about OpenMP offloading. That's a directive-based approach. We'll talk more about that later this week as well. And then OpenACC, which has been one of the more popular ways to use a pragma-based language to offload calculations. So let's get into those. So with CUDA code, we can convert the CUDA code, and basically same process as C. We're going to replace all the CUDA directives with HIP directives. And so then you just have to call those routines from Fortran, which you should already have if you're calling the CUDA routine. So that's a fairly straightforward process. Now, when you do convert it to HIP, you can now run it on both NVIDIA and on AMD GPUs. So we talked about this before. It's the same HIPify commands. You have to compile the HIP code with HIPCC and the Fortran code with the Fortran compiler. HIPFort was developed to make it a little bit easier to port new Fortran codes over to the GPU. And basically, if you want to do you have a pure Fortran code, you want to convert it over, just like we were doing with writing new HIP code, we need functions that are callable from C. So HIPFort provides all these functions, and they're all wrapped already, so you can just call them. So let's say HIPMalloc, HIPLaunch, all of those have been wrapped in, so they can be used in from a Fortran code. You still have to write your kernels in C, but it makes it much easier to convert your Fortran codes over to running on the GPU. And if you use HIP, you can run on both AMD and NVIDIA GPUs. ROCm will only run on AMD GPUs, just like with our discussions about HIP earlier. So HIPFort is part of the ROCm software package. It is now installed with part of ROCm starting with 5.4. So you may have to install it yourself. It's fairly easy to do, and the example shows how to do that. In the future, you may be able to call it directly. So you need to have the ROCm path set. It is forwarding on me, so excuse the confusion. So you need to have the include path set and the load library path set, but then it is just compiling the code, much like you would compile your Fortran code. So you can clone the HIPFort repository and add that location to your path as a user install, and then you can use that routine. So for CUDA Fortran, there is no direct equivalent. And so for those, you're going to want to convert manually over to using HIPFort and wrap your kernel. So you have to use the ISO-C bindings that have been introduced into Fortran for interoperability between Fortran and C. And that's not extremely difficult, but it is a tedious process. So using the HIPFort interfaces makes that a little bit easier, since ISO-C bindings can be a little tricky to do correctly. So let's look at our HIP launch kernel wrapper. So this is how you would launch a kernel on the GPU. We're going to call this launch routine from Fortran. So we create an interface, call it launch, and it will invoke the HIP launch kernel. So now from your routine, you can just call launch. Now, what does this look like in your routine? Well, here's our example that we're going to do. We're going to build HIPFort, and there are instructions in the HackMD to do this. And this exercise will be towards the end here. And since we'll be running out of time, it'll probably be on your own time if you're interested in the Fortran pathways. So you can build this library, put it in your path, and then just use the HIPFC compiler to compile this HIP implementation. And let's look at those codes to see what they look like. Okay. I'll pull up those codes in just a minute. So there's a Lunch and Learn series by Joe Schoonover where he shows how to port a fairly complex fluid code to HIPFort. And you can watch that presentation at this YouTube link. And Alessandro, one of our staff members, has also talked about HIPFort and how to use it at FortranCon. So those may be of interest to you. So I'm going to move on to OpenMP offloading. So we've talked a little bit about this for all languages. In this presentation, we're going to talk a little bit about the Siemens compiler and what support is available. So ROCm has what is called the AOMP compiler, which is the AMD OpenMP compiler. It has support for OpenMP and is pretty good for C and C++. It's lagging a little bit in the Fortran interface. And so you can get a more recent one with this pre-release version of AOMP if you're running into difficulties with it. But for better support in OpenMP and as a additional benefit, OpenACC, the GNU compilers are adding support for the MI100 and MI200 series. Now, that support is being upstreamed from Siemens work. And so, as with each release, they're providing more and more support. So if you want to go to the upstream releases where you can get the latest stuff that is a little bit ahead of the GCC releases, we can go directly to Siemens and download their compiler. They're releasing it on about a 3-month sequence, and right now they're working on functionality. By summer, they hope to be addressing most of the performance issues, but compilers do lag a little bit behind the performance that you can get from writing directly in HIP or some lower level language. If you're on the Cray systems, you have other support for OpenACC and OpenMP. So Cray was one of the first that established the OpenACC standard, and their Fortran compiler still is one of the best implementations of OpenACC. They haven't quite caught up to the latest standard. So some of the newest features may not be there, but they do have a very mature implementation. Their C++ compilers have switched to being based on LLVM. And they have the support for OpenMP and OpenACC through LLVM. LLVM really hasn't implemented OpenACC yet, though they have said that they would do that in the future through translating it to OpenMP. So I think we saw this slide earlier. It does help to know what the hardware has built into it, so that you know what sizes to put if you're going to customize or try to optimize your directives. Generally speaking, we do not recommend tuning these parameters initially, and because it does also affect portability. But if you do that, if you do try to optimize some of your kernels, these are the kinds of things you want to be aware of. So here is an example of a Fortran vector add with OpenMP. And so let's first just look at this and see that it's fairly standard code. If we ignore the OpenMP directive, we basically have a loop where we are adding the vectors A and B, and the result is C in the vector C. And so how do we translate this to a code which runs on the GPU? By putting this OpenMP directive in front of that loop, you can tell it to target a GPU device, or even a different kind of compute device. You're telling it to offload it to that device. You're telling it to create teams, distribute the work, and do it in parallel, and do a do loop. The map directive tells us that we are going to copy over to the GPU the A and B arrays, and we're going to copy back the C array. And so just by that one command, you now are running on the GPU. The kernel itself, this do loop, will be much faster, but now you have to transfer data back and forth. And so the way we usually proceed with OpenMP is we start moving the more compute intensive over to the GPU, and then slowly expand the region, so we're eliminating the data movement as much as possible. So here, the time is going to be dominated by the moving the data over to the GPU and then back. Now, you might try this as an exercise to extend that parallel region to the initialization loop, and perhaps even figuring out how to allocate memory on the GPU so that you don't have to copy the original data over. But you can see it doesn't take a lot of lines of code to convert a standard Fortran code over to running on the GPU. C and C++ are similar. But I do want to warn you that it can be a tedious process to extend these parallel regions and get the whole code running on the GPU. It doesn't take a lot of lines, but it can take a lot of work to move parts of your code over. And make the biggest confusion is you've got data on the GPU, you've got data on the host, and which is the most current, and making sure you've got the right one that you're working with. In complex code, that can be a difficult process. So to try this example out, you would load the AOMP compiler. You have to set the Fortran compiler to Flang in the AOMP path. And then you would just go ahead and compile the code like normal. I do sort of recommend, like Jose did earlier, that you try turning on some of these debugging flags when you're first experimenting with things, so you can make sure it's running on the GPU and find out what kind of problems you have. Here are two different ways to set flags to get more debugging output. And then our makefile is going to add the FOpenMP and the offload architecture. We're going to grab from the device what the GFX number is for that particular model. In this case, it's going to be the 09A, I believe. And then you just add that to your Fortran flags and load flags, and you need to add them to both. And then you build the code and run it. There's a couple exercises in the HackMD to try these out. You can try both the OpenMP and the OpenACC. There's examples for each of those with C and Fortran. So the GCC compiler right now, the default one on the system is not built with support for the AMD GPU. So it will run, but it's not running on the GPU. You have to go through a special process to get the GCC compiler built with support. You can load the Siemens compiler using the module for Siemens, and that will run on the GPU successfully. Similarly with AOMP and the HPE compiler. So we have several options today to how to run offloading on the AMD GPUs. If you are on a Cray system, I would kind of recommend the HPE compiler at this point and testing out the AMD compilers as they get more maturity. So OpenACC, it's very similar to the OpenMP standard. So what compilers support OpenACC? Well, the GCC compiler, the default built into the operating system, does not support OpenACC or OpenMP. Siemens does, and the Cray Fortran compilers do. So basically, if it's a GCC-based compiler, it will have support if it's built and installed correctly. LLVM are going to support OpenACC at some point, but they do not have that implemented yet. So what is the difference with OpenACC? Well, the directive looks a little bit different. So we have an ACC parallel loop directive, and we do a copy in instead of a map, copy in, copy out. Actually, OpenMP is now adopting this loop directive in later versions of the compiler, partly because their directive just got fairly long and had complications and portability issues. So they are also, you can also use the loop directive there. Otherwise, it looks exactly the same. And so there are a lot of projects that have implemented one version in OpenMP or OpenACC and then converted it over to the other with simple macros or other techniques. So if you want to try these examples, here's the directions for the for the Siemens compiler. If you do a module avail, I think it's called Siemens on the ACP system. And you'll want to set the FC variable so that it points to that compiler. Now, their compiler is, they have a very long name for the Fortran compiler. ACP has renamed it to just GFortran with a soft link. Other places have done something similar. But that's what you do. and then you just use that make file and run the code. Now, there's different options for verbose debugging for the GCC-based compilers that I show here. GCN suppress host fallback says don't let it run on the host, even if I can't run on the GPU. That's somewhat to try to make sure that it's running on the GPU, or to use GCN debug equals 1 to see that it has properly run on the GPU. So here's the make file for that OpenACC version. You'll see that you use the -f OpenACC, and the offload is a little bit more complex for the Siemens compiler. So we have two options with OpenACC. We can use Siemens or the HPE compiler. For Cray, there's a different debug flag. You may want to try to use this Cray ACC debug flag. So you can try those exercises, and you can try expanding that region to include more of that simple code, and then you could try testing your own OpenACC Fortran application, and you can report any issues with that, and we'll pass it up the chain. I do strongly recommend trying out just a very simple program to make sure your tool chain is working before you throw it at a big complex application. So summary, many features are still being added to these compilers. So I recommend using the latest compiler version you can get. Expect it to be improved with every release. Performance will be improving, so don't expect a stellar performance out of the box with your first tries using these, but they should be improving quickly. OpenMP is getting stronger development support, so if you're looking for a long-term path, you might choose OpenMP because it's getting more focus from LLVM and many other compilers. And please report to anyone in this AMD presenters compiler issues, and we'll pass them up the chain and try to make sure they get addressed. They are kind of overloaded with the amount of things they have to get implemented and optimized. So some patience is suggested, but do also tell us what the priority of the compiler issue is. We are particularly focused on functionality right now, just to make sure that any code would compile with the compiler, and optimization will come down the road. HPE compilers have been around longer, so if you have those available, you might, especially in the short term, focus on using those compilers. So you often get warnings and errors that are reported by the compiler or during the runtime. It can be difficult to understand what they're telling you. So that's actually one of the focus areas that we want to make with the compilers, is better error reporting, especially during the compile step. But you can see, like, you'll start to see the pattern. And for example, this error, memory fault, it's trying to access memory and it's not there. So likely the data is just not present on the GPU. I see this error in different forms from different compilers, that the host region overlaps, and that means it did not get deleted, released, and then copied properly back over. And so that can be a very confusing error message. You'll also see a lot of warnings. Actually, that's good at this point. Feedback from the compiler is really helpful when you're working on code. But if you see something that doesn't make sense, we'll go ahead and report it. With that, that's the end of my presentation.
Perfect timing. It's 5 o'clock.